that's
The first down.
All right, so I'm just going to review for the screencast that when you have a constant divided by infinity, that term is going to go to 0. So the limit as x approaches infinity of 5 minus something that approaches 0 will be 5. Same thing with negative infinity, it's still going to be 5. All right, so today we're doing section 2.6, which is limits at infinity and how they relate to horizontal asymptotes. All right. Uh-oh, I have hiccups. All right, we all good? Mihika, are you good? Yeah. So, don't write this. All right, so this is just a little visual here. So, when x is approaching infinity, we're talking about numbers that are huge, right? So, when x is approaching infinity, so for this function here, we have x squared minus 1 over x squared plus 1. Well, if x is just 0 and you plug it in, you get negative 1, right? But what they're showing you, this is a textbook thing. So the book is showing you that as x goes up to like 1,000, you take 1,000 squared. What's 1,000 squared? It's 1,000,000. Okay, so anyway, you take 1,000,000 minus 1 over 1,000,000 plus 1, right? When you get up into these giant numbers, like million, billion, trillion, and we're like just tapping the surface, right, of these gigantic numbers, the other stuff really becomes pretty insignificant. Like if I say, Keegan, I'm going to pay you $1 trillion minus 1, would you be like, oh God, $1, you know? No. Like you'd be okay, yeah, right? Yeah. So the minus 1 really doesn't matter that much. When you're getting paid $1 trillion minus 1, you can live with the minus 1, right? Okay. So $1 trillion minus 1 is essentially still $1 trillion. Okay, so when we get into these giant numbers, the terms that aren't what we call leading terms, the terms and leading terms in math mean the terms with the biggest exponents, right? So the terms that are non-leading terms become irrelevant, and we're just looking at the leading terms. So like for this problem, when you get into giant numbers, it's as though those are gone, and you're really just looking at x squared over x squared, which is just something over itself, which is why you end up approaching 1, right? So as x approaches infinity, this function approaches 1. You don't have to write this down. But as x approaches infinity, this function approaches 1. As x approaches negative infinity, it's the same thing because it's just negative infinity squared over negative infinity squared, right? Which is still just going to approach 1. So the limit as x approaches infinity and negative infinity, they're both 1. That means that y equals 1 is a horizontal asymptote for the function. Don't worry, we're going to write this formally in just a second. But so if you look carefully at the actual graph, see how like as x approaches infinity, the graph flattens out at y equals 1, and as x approaches negative infinity, the graph flattens out at y equals 1. Okay. A horizontal asymptote is a description of end behavior, right? What's going on way out here at this end and what's going on way out here at this end. That's what a horizontal asymptote is. It's saying, if we have one, it's saying, hey, out at either this end or this end, the graph flattens out at some y value. That's called the horizontal asymptote. How do we find it? We use limits to find it. Okay, you guys have learned techniques. The techniques are based on limits. So I'm going to show you the algebra and the calculus behind all the cute little tricks that you learned to find horizontal asymptotes today. So first, quick little discussion of graphs and possible different types of horizontal asymptotes. So one thing I want you to remember is that a horizontal asymptote is not an electric fence. You can cross over it, right? You can go up and approach it from the top. You can down and approach it from the bottom. Or you can like cross over it a whole bunch of times, right? All of these are fine. And all of these functions would have a horizontal asymptote at whatever L is. So they're just calling it y equals L. So this guy flattens out towards L from the bottom. This guy flattens out towards L from the top. This guy flattens out towards L, but he just keeps switching signs, but that's okay because he's still flattening out towards L. Does that make sense? Okay, so L, y equals L would be a horizontal asymptote, and vice versa for all of these graphs, the limit as x approaches infinity would be L. Okay, same thing in the other direction. So in the other direction, if we flatten out, you have a horizontal asymptote. Same thing, top, same thing. It's all the same, right? Okay. And we would say, hey, for these, you still have a horizontal asymptote at L, and the limit as x approaches negative infinity is L. So that's going to take us to what we're actually going to write. Wait, I'm going to put a shade up. It helps if there's too much to look at. And so we're going to put a shade up so we can focus on the right stuff. So y equals L, this is what I want you to write. Y equals L is called a horizontal asymptote if the limit as x approaches infinity is L, or the limit as x approaches negative infinity is L. Either one. If either end flattens out at a specific y value, then that y value is considered to be your horizontal asymptote. It can be both, but it doesn't have to be. It could just be one, or it could just be the other, or it could be both. Does anyone know what if means? Ooh, wait, I want to get your name right. I think I know it, but I don't want to say it and be wrong. Okay, so Nidhi.
Oh, it means if.
It does mean if and only if. That is awesome. Did you guys, have you learned that, all of you learned that before?
Yeah.
That if means if and only if? What does if and only if mean?
Like, yeah.
It's a what? Jennifer, say it.
It's a biconditional.
That was so beautiful. Oh my gosh, you nailed it. Okay. When you have an if-then statement, that's called a conditional statement. You learn that in geometry, right? When you first start your cute little T-chart proofs, right? Do you guys do little proofs in geometry? Okay. So when you first start, that's like your little intro to like Little League proofs, right? So when you do those little geometry proofs, you start learning statements like, did you guys learn things like inverse and converse, and did you learn contrapositive? No? Okay, all kinds of fun stuff, right? All those words go with conditional statements. There's a whole branch of mathematics studying how those kinds of things work. It's called truth tables. If you ever get to have a time in like upper level math where you get to study truth tables, they're really fun. If P, then Q. If not P, then not Q. If not Q, then P, right? Like which works with what, right? So anyway, and it's all doing the inverse and the converse and all that kind of stuff, but instead of with words, it's like letting letters represent the statements, right? In generic statements. So kind of fun. Anyway, I digress. So this statement would be called a biconditional statement. A conditional statement means if this is true, then this is true. A biconditional statement says if this is true, then this is true, and if this is true, then this is true. What that means is it works in both directions. It means this implies this, and this implies this. So when we write a conditional statement, we write it with like an equal sign and an arrow. If y equals L is a horizontal asymptote, then either the limit as x approaches infinity or negative infinity is L, right? In this case, it's an if, which means it's biconditional, which means if the limit as x approaches infinity or negative infinity is L, then y equals L is a horizontal asymptote, right? It works in both directions, so we signify it with a cute little double arrow with an equal sign in the middle. So if you ever see this symbol, the symbol means the same thing as if, and both of them imply that it is a biconditional statement. It works in both directions. Okay. Well done, Jennifer. That was awesome, right? Okay. And Nitty for knowing that it was an if and only if, right? So it took some prodding with first period to get them to say that. So one student remembered finally the if, what that meant. So well done. All right. So what does this mean? It means you could either be flattening out on the right, the right, or the left, or both. Either way, if you're flattening out at a y value, that y value is a horizontal asymptote, and vice versa, right? Okay. So it helps if you know the rules for horizontal asymptotes. Now in, I think pre-calc, it might be algebra 2. I think in algebra 2 is when you first learn the rules, the tricks for horizontal asymptotes. So do you guys remember if you have what's called a rational function, which is a function that's a fraction? Do you guys know rational function? We had this talk this morning. Rational, I'm going to write it on here. Rational. Okay, what do the first 5 letters of rational spell? Ratio, right? A rational function is a function that contains a ratio, right? Okay, so a ratio is something that can be written as a fraction. It's a comparison of two quantities, right? So a rational function essentially is a function that's a fraction, right? Now, for our intents and purposes, we're only talking about rational functions right now where you have a polynomial over a polynomial. Now, I had students who actually didn't know what a polynomial was in first grade, so let's make sure we all know what a polynomial is. Polynomial is x's to powers being added together, right? So like if I had, x squared minus 3x plus 2, that's a polynomial. I had a student this morning who came in and said that she thought that was not a polynomial because she thought you had to have every single x in descending order. You don't, right? The coefficient can be 0. That's okay. As a matter of fact, for our purposes, that's a polynomial, right? Technically, it's a constant. But we're going to call it a polynomial because it's just like 0x minus 2, right? And you see it was negative 2x to the 0. So x's to power, a string, a sum of x's to powers over a sum of x's to powers. No roots, no exponentials, no e's, no logs, nothing like that. Just nice normal polynomial over a polynomial. All right. So if you have a polynomial over a polynomial, each polynomial has a degree. Does anyone know what the degree is? Yes, very good. Wait. Someday I am going to learn your names. Okay, Anisha.
Yeah.
Okay, highest exponent. The degree is the highest exponent, right? Okay, so the degree of the top and the degree of the bottom are what we look at. If the degree of the top is smaller, so say you have an x squared over an x cubed, right? The degree of the top is smaller, then you automatically have a horizontal asymptote at y equals 0. Right? So if the degree of the top is smaller, so I'm calling like A be the top and B be the bottom. If the top is smaller than the bottom is bigger, then your horizontal asymptote is at y equals 0. If the degrees are the same, then your horizontal asymptote is the quotient of the leading coefficients. So the coefficient of the term with the highest exponent. Do you guys know the coefficient is the number in front? Okay. All right. So if they're the same, it's the quotient. The horizontal asymptote is the quotient of the leading coefficients. If the top is bigger, there is no horizontal asymptote. What does that mean? When there's no horizontal asymptote on a rational function, it means it's either going up to infinity or it's going down to negative infinity. These 3 little rules should ring a bell. Do they ring a bell?
Yeah.
Okay, good. All right. If you can remember these rules, it will make a lot of your limits be 2 seconds. But remember, we're only going to use these when you have a polynomial over a polynomial. There's one other gift. When you have a polynomial over a polynomial, you have one horizontal asymptote, and it is the limit in both directions. So whenever you have a polynomial over a polynomial, the limit as x approaches infinity will be the same as the limit as x approaches negative infinity, and they're both going to equal your horizontal asymptote. All right, does everyone have whatever they need to write for this to help refresh their memory? Nope? Okay, I'll give you another moment to write. Okay, so I have on the board 4 examples. Using the horizontal asymptote rules, I want you to find the value of each of these limits, and then you're going to state your horizontal asymptotes for there's 2 different functions represented with 2 limits per function. So you can go ahead and write down the 4 problems. Write them down first, and then I'm going to make you do them like really fast. We're going to do speed horizontal asymptoting. Yes, Ari.
Can you read the numbers?
Limit as x approaches infinity.
Okay.
And then, can you see the function?
Yeah.
Next one, limit as x approaches negative infinity.
All right.
Same function. Next one, limit as x approaches infinity. And then the last one is a negative infinity.
All right, thank you.
You're so welcome. Charles, you don't even need that laptop up. I haven't even posted the notes to Schoology. You can close it all the way. There we go. Good. All right, everyone have them written down. Close, okay. I don't want you doing them, just writing them, right? Unless you've already done them. Once you know your rules, you should be able to do these almost as fast as you can write them. Okay, I'm going to give you 30 seconds to do all 4 problems and check your answers with your groups. Are you ready? Wait. Begin, go. Does anyone need more time? It's still only been 20 seconds. I had groups done in 5 seconds. Okay. All right.
Like, start at the top.
Sweet Ian, how are you doing? Are you? Yeah. Okay. What did your group get for the first limit? 0? Why 0? Okay, what is A? What's the degree of the top? That's the leading coefficient. It's 1. No, good. That's good. See? Self-correcting. That's great. What's the degree of the bottom? You got it. See? You got it. Right? We get by with a little help from our friends. We all need it. Okay. Degree of the top is 1. Degree of the bottom is 2. Remember, degree is your highest exponent, right? So if the bottom is bigger, then the limit goes to 0, which is the same as the horizontal asymptote. All right. So, Pranav, what did your group get for the next one? Also 0? Is that a question or an answer? That's an answer? 0? Okay. Yes. Why? Yeah, same thing, right? Infinity, negative infinity makes no difference. With these simple rational functions, the rules apply no matter which infinity you're pointing to. So for this, we would have a horizontal asymptote at y equals 0. And that would be it for both of these. I could one asymptote for both of them. It's just an asymptote for the function. All right. Let's see. Emma. Hi, Emma. What'd your group get for C?
-3.
-3 halves. Okay, first tell me what you noticed about the degrees. They're the same, right? Degrees the same, top and bottom. 1, 1. Good. So how did you get -3 halves?
You would take the leading coefficients of both of the highest degrees and then you divide them.
So wouldn't the leading coefficient on the bottom be 5? No? Are you sure?
Take it from the degree for the one the highest degree.
Very good. You take it from the term with the highest exponent, right? Any questions on how Emma got this one? You're all good? Good. You got it. As well done. Okay. All right. Kirthana. Hi, Kirthana. Okay. What'd you get for the last one?
I got -3.
What? Again? Are you sure? Okay, yeah, do it. Okay, good. So because of that, Megan, what's the horizontal asymptote for y equals 3x plus 1 over 5 minus 2x? Y equals -3. Are we all, does everyone understand just the basic rules? Degree stuff. Okay. All right. Now, I'm going to show you, don't worry, I know we haven't done the infinity ones yet. We'll get there. But first I'm going to show you why this is true. So we're going to do this problem, and then I'm going to show it to you again using some algebra so you understand where those rules came from and why they are true, right? Did you ever ask your teacher, like, why? No? Oh, you just accepted it blindly?
Yeah.
Okay. All right. So, let's see, Keegan. Take a look at this first one. What's the degree of the top?
2.
What's the degree of the bottom?
2.
Are they the same?
Yeah.
So what's our limit?
8 ninths.
We nailed it, right? Okay, 8 ninths. Does everyone agree?
Yeah.
Okay, good. Because I said you nailed it, that implies it was right. All right. So why is it 8 ninths? So there's an algebraic method for finding these limits that some professors make you do every single time when you're taking calculus. So, and I had one of those, but I am not one of those. So, but I have experienced one. Now, there's value to understanding why it works, but I feel like just doing just grunt repetition over and over doesn't serve me any purpose. As long as I understand the why, I don't need to do the long method every time. So, anyway, here's why. So if you divide the top and bottom by the highest degree of x, right? Really, instead of dividing, I'm going to think of it as like multiplying by 1 over x squared, top and bottom. If you multiply the top by 1 over x squared, well, what does the first term become? 8 plus 1 over x squared, right? Let's look at the bottom. What does the first term become? 9 minus 3 over x minus 5 over x squared, right? When the degrees are the same, you're going to end up with all the terms that, remember x is going to infinity, all the terms that aren't the leading terms will have an x on the bottom. And those will all go to 0, right? And all you're left with are your leading coefficients. If the bottom is bigger, like just doing a quick simple one, if we had the limit as x approaches infinity of 8x plus 1 over 9x squared minus 3x, right, whatever, right? Then if we divide, it's easier actually in some of these not to divide by the highest, but by the height. Let's just divide by x. If we divide by x, so times 1 over x, so we get, so on top we get 8 plus 1 over x over, let's see, 9x minus 3, right? 8's going to stay 8. 9x is going to infinity, right? This thing's going to be 8 over infinity. What's 8 over infinity? It's 0, right? So you kind of finagle a little bit with your multiplying and your dividing. But anyway, that's kind of the why. You don't have to do that. I will never ask you to. You can do this, and I'll be a happy camper, right? Okay. All right. But sometimes it's good to know the why. Okay. Let's get into the ones that actually don't have horizontal asymptotes, like these. So now the top is bigger, right? So if you think about it, let's, you write the problem, but I'm just going to show you real quick. If we multiply the top and bottom by 1 over x, we end up with 3x plus 1 over x over 2 minus 5 over x. So now those guys are both 0. You have 3 times infinity over 2. What's 3 times infinity over 2? Infinity, right? Okay. So anyway, but that's not what we're going to do. When you have, again, polynomial, x approaching infinity, degree of the top is bigger, you can't just write no horizontal. Well, if I ask you what's the horizontal asymptote, yes, you can just write no horizontal asymptote. But if I ask you the limit like this, and I say, hey, what's the limit? You can't just write none because there's an answer. So you have to, now it's going to be infinity or a negative infinity. This is another one where you're checking the signs. So just plug the infinity in. Is 3 times infinity squared plus 1 positive or negative? Positive. So I'm going to put a little plus here. Is 2 times infinity minus 5 positive or negative?
Positive.
Are you sure you're subtracting 5?
From infinity.
From infinity. Okay, yeah, it's still positive. Okay, does everyone understand that? Okay, so still positive. What's a positive over positive? This guy's going to positive infinity. Let's look at the negative now. What's 3 times negative infinity squared plus 1? Is that going to be a positive or a negative? Positive. What about 2 times negative infinity minus 5?
Negative.
That's going to be a negative. Positive over a negative is a negative. This guy's going to negative infinity. This is one of those functions that's going to like point down on this end and point up on that end, right? With some stuff happening in the middle. Right, that's going to. All right. We had another teacher who used to name all of his function families after celebrities, right? And so like you had the John Travolta. But anyway, all right. Okay, it's Thoughtful Thursday. Okay, moving on. What if the function is not a polynomial over a polynomial? We have a lot to learn in this slide. Here we go. So we have this beautiful rational function, but it's not a polynomial over a polynomial. It's a radical over a polynomial, right? Your WebAssign calls it a root over a polynomial. So when we have a radical over a polynomial, you have to test, whenever you have not polynomial over polynomial, you've got to check your limits from the left and the right, towards the left and towards the right. So you have to check your limits at negative infinity and positive infinity, because you might have two different values. And if you have two different values, you have two different horizontal asymptotes. So what's the highest number of horizontal asymptotes you can have? Any? Can you have 6?
Because it has to be, it's n behavior. Wait. It's n behavior.
There's only 2 ends to a function. The most you can have is 2, right? So you can't have more than 2 because you only have 2 ends, right? Okay. All right. I'm going to tell you the answer first, and then I'm going to show you how to get it. Actually, I'm lying. I'm going to tell you one of the answers. Oh, whoops, I shouldn't be putting f of x equals. Sorry. I'm listing horizontal asymptotes. So one answer for our horizontal asymptote is y equals root 2 over 3. Take a moment and see if you can figure out why that's true. Just digest, mull for a minute, please. I'm giving you 30 seconds to mull.
I see it.
Oh,
Those are, yeah.
yeah, because we take, wait, actually,
The one is like, well, because like
It
if
doesn't
you,
matter.
because it's x plus
wait, but
1
can you split up
over
the
your
root?
can you split up the root? Yeah, I think.
Okay.
You can't split up.
Okay, mulling time's over. Let's walk through the math behind this. So I'm going to do the limit as x approaches infinity of the square root of 2x squared plus 1 over 3x minus 5.
I get how she got it.
When you are approaching infinity, right? Infinity. The non-leading terms are totally irrelevant. They have no say on what happens with this function as a whole. So, you are absolutely mathematically within your rights to drop them.
Oh.
Now, we've got the square root of 2x squared. The square root of 2x squared is the same thing as the square root of 2 times the square root of x squared. Now, when x is positive, the square root of x squared is just equal to x. So this is the same thing as root 2 times x over 3 times x. Same degree top and bottom. Now we're just polynomial over polynomial. Quotient of the leading coefficients, done. So my advice to you, if you have some sort of a funky limit at infinity situation and you're not sure what to do, always start by dropping any non-leading terms. Just get rid of them, right? And then see what you can do from there. However, that's not the only answer. We have 2 horizontal asymptotes for this function. Let's see what happens at negative infinity. And that's going to lead us into a whole separate lesson that Ms. Grunwald has already taught and I have not. So we had a little discussion about it. I slacked off. So I'm going to bring it back around. So here we go. First thing I'm going to do, though, drop the non-leading terms. All right, we're going to take a side step and talk about the square root of x squared. The square root of x squared is not x. Square root of x squared is the absolute value of x. Why is it the absolute value of x? Because if you plug in a positive number in here like 5, 5 squared is 25, root 25 is 5, right? 5 just stays 5. Okay. But if you plug in a negative number, like -5, you get -5 squared is 25, square root of 25 is 5. The negative number becomes positive. Positive stays positive, negative becomes positive. So the square root of x squared is the same as the absolute value of x. Now, in calculus world, we cannot do anything with an absolute value function. So what do we have to do with all absolute value functions? We have to write them as piecewise. We write them as a piecewise function. We love piecewise functions. How do we write absolute value of x as a piecewise function? I'm going to walk you through some steps, and then we're going to talk about this a little bit, and then I have to make a confession to Ms. Grunwald because we'll just talk about that later. Okay. So, first thing you do to write as a piecewise is you take what I lovingly call the guts of the absolute value. So when you hear me say guts, guts are Mr. Thomas, who was like the best math teacher in the world. So he retired. It's his word for the input or the argument of the function. It's the stuff inside the function, right? We call it the guts. So you're going to hear me use the word guts all year. So the guts of the absolute value in this case are x. It's just x, right? You set the guts equal to 0, and you solve for x, which in this case is not too hard because it's x equals 0. This number becomes like your handoff point. So this number is what goes there. For an absolute value, because absolute values always hand off at the same spot, right? Like you've got, like your V or whatever, right? The equals sign can go on either one. Doesn't matter. Greater than, less than, makes no difference, just not both, okay? So I like to put the equals with the greater than because I'm a positive person. So here we go. All right, so we've got our equals down. Now what goes inside? One of these is going to be the same as the guts, and one of these is going to be the negative of the guts. And your job is to figure out which one's the positive and which one's the negative. How do you know? Pick a number in this interval, right? Okay, so I'm going to learn some names. Zuhair, pick a number bigger than 0. 4. So if I plug a 4 just into the guts, just in for x, is it positive or negative? Positive, this is the one that stays the same. You just drop the absolute value. Because the absolute value is not doing anything for 4, right? It's just saying, hey, it's 4. It's still 4, right? Okay, so you don't need it. It's moot. Okay. So now, let's see, Ishan, pick a number less than 0.
-4.
-4. If I plug a -4 in for x, do I get a positive or a negative?
Negative.
A negative. When you get a negative, you got to multiply the guts by a negative. Because the output then for the absolute value of -4 would be -4 or 4. Right? It's basically, you're taking a negative and multiplying it by -1 to make it positive. This is absolute value as piecewise. If you're in this room and you need to write an absolute value as a piecewise, I have a poster. I made this poster like 18 years ago, and it has traveled with me around the country, right? So, because I got so tired of reteaching this over and over. So whenever you have to write an absolute value as a piecewise, feel free to walk over and look at the poster, okay? So set argument equal to 0, and so argument is guts. Set equal to 0, solve for x. Here's an example, right? So we're doing this one. There's our example. Make this your splitting point, right? That's your handout. You can move the ducks, right? Handoff point. And then plug in numbers into the guts. If you get a positive, you just rewrite. If you get a negative, you multiply the guts by a negative. That's all there is to it, okay? All right, let's get back to our problem now. Because of this, when x is approaching negative infinity, the x's are going to be really, really negative. So the square root of x squared is going to be equal to negative x. So you have to rewrite your limit as root 2 times negative x over 3x. So what is the actual value of this limit? Negative root 2 over 3. And this function actually has two horizontal asymptotes, one at positive and one at negative. All right, that's a lot of time on that problem, but that's okay, it's worth it. All right, any questions on this? Moving right along. Okay, so take a minute. I give you 1 minute to find the horizontal asymptotes for this function. Practice, go. Let's do. Okay, because we're short on time, I kind of worked it out while you guys were working. How does that fit? You okay? So whenever you don't have polynomial over polynomial, you have to check the limits for both. You got to do the infinity and the negative infinity because it's very likely you're going to get two different answers. Okay. All right. By the way, do I have to rationalize this? No, nobody cares. Okay, moving on. All right. Some problems, once in a while, you have a problem that you have to think about it. Like you actually have to think. So, because we are short on time, well, you know what, we have 30 seconds to think. So I'm going to give you 30 seconds. I just want you to mull on this for a minute. And I gave you a hint. Sign is stuck between -1 and 1. So mull with your groups for a minute. Because you're not going to do this algebraically.
Still goes in between.
I feel like I actually brought this over. No, it doesn't. It's just
What
if it also like
Because it's going to be a number between -1 and 1.
Is it?
Yeah, because it's always
Oh. It'll be 0 over 0.
But
So it's like side of 1.
Wait, hold on. Wait, sorry. But like,
Do higher. What do you think this limit is? It's 0. And I heard him describing something that was so awesome that I had to run over and just listen in for a minute. That's why I'm sorry I called on you twice today, but I it was just too awesome for me to pass up. So, it is 0. But we're going to talk about it, and then I'm going to tell you what Zuhair came up with. So, sine oscillates between 1 and -1. It's never going to all of a sudden pop up to 22, right? It is always between 1 and -1. We're not going to get into the reasons why right now, but it is. Okay, so you've got a number that is stuck between 1 and -1 divided by infinity, right? It doesn't matter what that number is, infinity's going to win, right? This guy's going to 0. Does that make sense? Okay. So now, what does the graph look like? This is that function that we saw that does this kind of a thing, right? So even though it changes sign all the way along, right? It's positive, it's negative, it's positive, it's negative, it's positive, right? That's okay because it's still flattening out towards 0. Even though it alternates in sign, it's okay as long as it flattens towards 0. So, and which is what you had said, right? Yeah, well done. Yeah, sorry.
So when it flattens out, it doesn't flatten out exactly.
Remember what a limit is. The limit says as x approaches infinity, what value is y approaching?
Yeah, so is it approaching from positive or negative?
This is only infinity. Infinity is only here. You can't approach infinity from the right. That's a good question. There's no such thing as a right-handed limit on infinity. There is only left. So as x, that is a really good question because you can't get to the other side of infinity. It's infinity, right? So when x is approaching infinity, we're only talking about from this side, right? And we're talking about what does y approach from this side. So you're right. You don't have a left and right-handed limit for these, and we accept that as being okay. Good point. Yeah. All right. Okay, this last slide, which is not going to be the last slide. Right now it's the last slide, but we're going to add one, and we're going to squish it in before core. This last slide looks complicated, and it's really fun. It's simple. It's easy. You're going to love it. So the last slide is a topic called comparative growth rates. And in your notes, I want you to write the words comparative growth rates. I know it's a lot today. Sorry, it was a heavy day, but we had to kind of squish in because we had a short class. For comparative growth rates, what it says is if you're finding the limit as x approaches infinity, and you have a function that grows faster over a function that grows slower, then the limit is going to approach infinity, or negative infinity if one of them is negative. But it's going to go to an infinity. Faster over slower means infinity. On the other side, if the limit, if you have a slower function on top over a faster growing function on the bottom, the limit is going to go to 0. Faster function wins. So the faster functions on top, the limit's going to an infinity. The faster functions on the bottom, the limit is going to 0. How do you know which functions are slower and which functions are faster? I've given you a little, it's not really a graphic, but I've given you kind of a little cheat sheet here. Logarithms are the slowest. Logarithms are the turtles of the function world. So logarithms grow slow. They're the slowest. They grow so slow that they look like they have horizontal asymptotes when they don't. They're just growing really slow. They're going so slow they look flat. Okay, but they don't. Next are polynomials and radicals. So these I kind of lump together. You look at the degrees. For example, if I have an x to the second over an x to the 8/3, this guy is growing faster. It's a higher degree. 8/3 is bigger than 2. All right? So polynomials and radicals, for comparative growth rates, you kind of lump together, and it's just whichever degree is bigger, right? But polynomials are still faster growing than logarithms, and no matter what, polynomials and radicals are always slower than exponentials. What's an exponential? It's where you have an x in the exponent, right? 2 to the x, 3 to the x, e to the x, right? Those are all called exponentials. And then the fastest function you've got is a factorial. Anyone know what a factorial is? Exclamation point. Yes, that's how you say it. Exclamation point. Those are the fastest. So I know the bell. We're going to go 1 minute beyond. I'm so sorry. 1 minute beyond. Okay. So for these two examples, very quickly, what kind of function? We've got 8x to the 5,000 plus 99999999999 over 2 to the x. Which one grows faster? 2 to the x. Exponential grows faster. Doesn't matter how big your exponent is. This is still a polynomial. This guy's going to win. It might not win for a while, but when you're going to infinity, you've got a while, right? Okay. All right. So since the bottom grows faster, this guy's going to 0. For this guy, we have a radical over a logarithm. Which one grows faster? The radical grows faster. So no matter what the base of the log is, doesn't matter if it's log base 8 or log base, 826, the radical's still going to grow faster. This guy's going to. All right. In your homework, so let's talk core. So the first question is, you have a problem in your homework tonight with a beautiful function called arctangent. Okay? Oh, that was a yawn. I thought that was like a gasp, like, oh, okay. So arctangent. So a quick review, just so you know what arctangent is. Arctangent is the inverse of tangent, right? So we know if the tangent of pi fourths, what's the tangent of pi fourths? 1. If the tangent of pi fourths is 1, then the arctangent of 1 is pi fourths. So in other words, the arctangent is the angle of the arctan, if the arctan is this, then the angle whose tangent is 1, right? It's the angle whose tangent is this value. So when you're doing an arctan, you switch, the input and output switch. It's an inverse function. You guys might also have written it like this, right? That's the same thing. Arctan and inverse tan are the same thing. Now, on the graph, tangent looks like x cubed, but it's repeated a bunch, right? Okay, so here's the thing. Arctan, so this is tan. This is negative pi halves. This is pi halves. So arctan, in order for arctan to be a function, do you know when you do an inverse that you like rotate and flip? You guys know that? Okay. Well, anyway, when you do an inverse, so the inverse, this is arctan, looks like this. So this is now negative pi halves, and this is now pi halves. So arctangent has 2 horizontal asymptotes, one at negative infinity and one at positive infinity, right? So that comes up one time in your homework. So just so you know, I'm going to tell you, and I'll tell Ms. Grimold I told you, this is not on your test. I didn't put any inverse trig on your test this time. There will be inverse trig in chapter 3, but not in chapter 2. Okay. And one more quick thing. If I ask you for the horizontal asymptotes, what do you think this limit is? I'm hearing a 0. This limit is 1. It's just like the polynomial stuff. It's basically the same thing, top and bottom. It's the quotient of the leading coefficients. Be careful, because e to the negative infinity, that's 1 over e to the infinity. Right? Negative exponent, you flip, right? What's this limit? Oh, whoops, I wrote limit. Oh no, I'm plugging in. I'm okay. Gosh, I almost thought about dropping on the negative. Negative 5 halves. 2 horizontal asymptotes. Whoa. Okay, that's it. Core time's your time. That's it. So there we go.